All right, my name is Raja, and today I'm going to talk about how one particular field of systems research, unfortunately one that's really related to my thesis research, is just doomed to failure unless we learn to build distributed systems and data centers that have much more predictable performance. So all of us in the room know that building distributed systems is all about trade-offs, right? There's no one right answer. Butler Lamson said this best in his intro to the paper Hints for Computer Systems Design, where he said, the designer usually finds himself floundering in a sea of possibilities, unclear about how one choice will affect his freedom or affect the size and performance of the entire system. Choosing the right metrics and axes to care about when designing a distributed system is an important yet really daunting task. But over the years, system builders have identified a set of metrics that are important: correctness, performance, reliability, and perhaps a few more. Power has recently become much more important. Optimizing one often results in trading off another. So the right optimizations differ based on a specific distributed system being built, but at least there are these really key axes that we care about. But perhaps there's one metric that we're ignoring more than we should when building large distributed systems and clouds, and that's predictability. As we build larger and larger systems, I think this metric is becoming more and more important. This is true for numerous reasons. For example, without increased predictability, the performance of large-scale workloads suffer. Also, our great dreams of automated management, a very popular research topic for the past decade or so, just won't be possible. So in this talk, I want to further pound in the importance of considering predictability as a key metric when designing distributed systems. And also, I want to say there's just no magic answer to achieving more predictability. It's just going to require really hard work during system development, testing, and maintenance. All right. So to be formal, what do I mean about predictability? The easiest way is to say that it means low variance. More generally, we should say low conditional variance. So in this graph, the x-axis shows some arbitrary metric, perhaps response time or throughput, and the y-axis shows the probability for a given metric value. So this blue metric distribution is predictable because the range of values it can take is pretty tightly bounded around its mean. So you pretty much always know what you're going to get. On the other hand, this yellow metric distribution is less predictable. The range of values it can take with decent probability is pretty wide. So it's hard to tell what value you're going to get at any given time. There's been a few talks and papers recently touting the increased importance of predictability, including a few here yesterday morning. At last year's AskPLOS, Luis Barroso talked about how it affects the performance and efficiency of very large-scale computing workloads. The setup is that you often have a client that must read data that's shared across many different servers. So though some servers might respond quickly, right, say around a microsecond here, it's really, really fast, right? Some respond slower, some faster, and some with average performance. The overall task latency will always be limited by the slowest server. If the server response time distribution has a really, really long tail, the slowest server could just be really, really slow, right? Here around 25 milliseconds. So basically, not only is overall performance slow, but the speed of the faster servers is being wasted. Predictability is also important for setting and enforcing strong service-level agreements. As a distributed service provider or cloud environment, you might be elated, right, that the average response time you can promise to a client is really fast, say around 500 microseconds, right? But when you specify your SLA, perhaps specified in terms of response times in the distribution's tail, which is really common, you might just be disappointed to find that your response time variance is so high that all you can promise is that 95% of your response times are less than a whopping 25 milliseconds. So this is a real problem. A couple of talks yesterday mentioned it. Also, a recent paper in VLDB Endowment measured such variance in cloud computing environments to see whether it's possible to even perform repeatable experiments within them. Their conclusion is, and I quote, "The variance on EC2 is currently so high that wall clock experiments may only be performed with considerable care." As distributed systems keep scaling, a third area for which predictability is becoming increasingly important, but perhaps it's receiving less mainstream attention, is a goal of systems research for many years, and that's automated management of large data centers and distributed systems. An example is a topic that's particularly close to me, or at least my thesis, and that's automated performance diagnosis. So over the past several years, there have been many papers published on automation and automated performance diagnosis. You're guaranteed to find one at least every FAST or NSDI or SIGCOMM and so on. But the funny thing is that despite all this research effort, most of these tools don't seem to actually make it into production environments. And the problem isn't so much the tools. Improving them can only help so much, right? Rather, one primary reason is the distributed systems and data centers you're supposed to operate on. The problem is that we've been building more and more complex distributed systems built on top of distributed systems, built on top of other distributed systems and services, without really considering whether these services have key properties needed for things like automation and strong service level agreements to work. Then we expect to be able to somehow layer automation on top, leading to what I call the cherry on top approach to automation. This sort of post hoc design methodology has been known for ages not to work for security, and it won't work for automation either. And also, I want to point out that this analogy holds for many of the previous examples I presented also. So why are automated performance diagnosis tools affected so much by variance? Well, first of all, most of these tools help developers diagnose problems by automatically localizing the root cause of a new problem from the numerous components in the system to just a few potential culprits. They do so for looking for suspicious deviations in key metrics, perhaps response times, throughput, CPU utilizations, or a combination of those across all the machines and services involved. Increased variance in these metrics causes problems. On the left, you see two sample distributions for an important metric, say response times or throughput, right? Made up of observed pieces of some unknown actual distribution, right? So there's some uncertainty about them. Specifically, do these two sample distributions actually represent the same underlying distribution or not? For these two sample distributions, it's pretty obvious that the underlying distributions are in fact different. They have very different means. Their variance around their means is very small, and they don't overlap much. So it's easy to tell that these things represent different behaviors or different things. On the other hand, the sample distributions on the right don't have these properties. Their means are still different, but they have really, really large variance, and they overlap a lot. So it isn't clear whether they represent the same underlying distribution or only differ at random chance, right? So it isn't clear whether they represent truly different behaviors at all. So to make the implications of the previous slide a bit more concrete, I want to spend a few times talking about the life of a graduate student versus that of a performance diagnosis tool. So here's our grad student, and here's a large distributed service made up of several distributed services in of itself. So it's a photo sharing app which communicates with a corresponding service within the data center, which in turn relies on many other distributed services, such as HBase and HDFS to work. So here's the service over here. So let's say the graduate student comes up with a fabulous new idea, an extremely fabulous new idea for improving the system, and implementing it yields a performance improvement of about 25% in average or mean response times, computed over a few repeated experiments. But when he looks at the variance or error bars across his experiments, though, they indicate that he really doesn't have enough data to truly tell whether he's improved performance or not. Here you can see the error bars overlap, which is an indication that he doesn't have statistical significance for his results. So the grad student has two options, right? He can run more experiments to try and obtain statistical significance and more confidence in his results, right? Or conversely, since he's a systems person, and since we heard yesterday from the 7 deadly sins of cloud computing talk, we don't tend to put error bars in our papers anyway. Perhaps he just removes them and publishes the paper and is really happy. Now, the life of a performance diagnosis tool is just so much harder, right? So let's say this tool is tasked with deciphering which machines or services are responsible for a reduction in end-to-end response times visible by the client for this entire set of services, right? The entire thing, right? So the way it usually works, is it compares the pre-degradation metric distributions it cares about with those after degradation within each of the services and machines involved, right? If it finds for a few of them the metric distributions are very similar. So here for this photo sharing service, it compares the pre-degradation metrics it cares about, shown in blue, with the post-degradation metrics, and it finds that these are really similar, right? So it's pretty confident that the photo sharing service can't be responsible for its degradation, right? And perhaps this is true for a couple of other services as well, the app itself, HDFS, and so on, right? But for other services, the distributions look kind of different. Their means are slightly different, but the observed variance is just too high to be sure. So it isn't quite clear that these are really different distributions or different behaviors, right? So now the diagnosis tool has this very difficult problem. which of these pink services with really high variance should the tool indict as the culprit, if any? Now, unlike the grad student, the diagnosis tool can't just ignore the underlying variance and guess. Doing so will yield either more false positives or false negatives, depending on the choice it makes on which services to indict. False positives are just really, really bad because they mislead the developer. They waste his time and effort and lowers confidence in the automation tool itself. False negatives are also bad because in these cases, the tool just isn't being useful. It's just throwing up its hands and saying, hey, I don't know what to do. Go figure it out yourself. Right? That's clearly not the goal of automation. Right? Also, unlike for the grad student case, in many cases in live production, the problem just can't be rerun to obtain significance or to obtain more detailed information about the problem. The data the tool has is all it has to go on, and all it has to go on to base its decisions. So the key takeaway here is that unless a distributed system satisfies some properties about predictability, the capacity for automated performance diagnosis is pretty limited. So if we buy that increased predictability is actually a good thing, right? What can we do to increase it? Unfortunately, I don't think there's any magic sauce involved here, except just plain hard work. Right? Developers must learn to treat variance of key metrics, like response times and throughputs, as very important in and of themselves. They must identify high variance areas of the system, functions, components, services, and so on, and make conscious, explicit decisions about what to do about their variance. And the answer isn't always to reduce it, because sometimes variance is a given. It might emanate from hardware that is difficult to change, for example. Also, sometimes variance is useful. For example, caches trade performance or variance for increased performance. It also avoids synchronized stuck states like TCP incast, where synchronized replies from data nodes overload the intermediary switch or router. But the key thing here is that these decisions about where to reduce variance, where not to reduce it, need to be conscious decisions made by developers. They need to be explicitly made. Finally, in areas of the system, for example, functions or components or services, where the developer decides the observed variance is useful or too difficult to reduce, you must strive to isolate the performance characteristics of these areas from the rest of the system. Doing so will increase the areas of the system for which good things can be reasoned about, like for automation and strong SLAs. So to help developers with this really difficult task, we propose a framework for helping them. It consists of a tool called VarianceFinder, which identifies similar behavior. For example, cache hits within the same machine would be considered the same behavior versus cache misses would be considered different from cache hits, right? With high variance, and localizes such high variance to just the services, components, or functions responsible. Also, we propose a nomenclature for naming variance sources, so as to help developers and system builders reason about what to do about these variance sources. There's a lot more detail about this framework in our paper, but for the purpose of this talk, I just want to go over the nomenclature. So here are the three labels I think that can be applied to variance sources in distributed systems and cloud environments. Inadvertent variance is unintentional and should just be reduced, right? It may be the result of spaghetti code. For example, a function that's poorly written or contains many different code paths, right? Each executing significantly different activity and having very different performance. It could also be a performance bug. For example, a hash table that incurs slowly increasing access times because it always bins data into the same bucket. It could also be due to greater than expected resource contention. Intrinsic variance is a result of fundamental properties of the data center, which are developed within which a distributed system is operating. As such, developers may not have the control necessary to reduce their variance. An example of this is a consumer-grade hard disk. There was a HotOS paper last year that showed that no such two disks display similar performance characteristics, even if they come from the same vendor and the same batch. Intentional variance is a result of an explicit trade-off made by developers and system builders. It may include schedulers that increase variance in favor of resource efficiency or lower mean latency, or it may be explicit anti-correlation added to avoid bad synchronized states, for example, to avoid things like incast. Micro reboots from the ROC work a decade ago are also an example of such explicit anti-correlation. So we're not reducing variance here. Once again, at least it's a conscious, explicit decision made by developers and system builders. So, this is kind of weird, right? The last two sources of variance we're saying won't be reduced or can't be reduced. So what can be done? To help predictability, developers should mark them in a way that their performance characteristics can be isolated or subtracted from the rest of the system. maybe by adding a set of log points or instrumentation points tightly around them, right, that automation tools and things that set SLAs can pick up on. Right? Doing so will increase the areas of the system for which automation can work, and things like SLAs can be specified. So I think there are a lot of open questions we face when we think about how to increase predictability and lower variance in distributed systems and data centers. For example, how much variance needs to be reduced to get the predictability properties we desire for different workloads and different systems? Basically, what are the right trade-offs for these different types of systems? We also need to understand the breakdown of variance sources within these distributed systems and data centers. If it turns out inadvertent variance isn't a dominant factor, and say it's intrinsic variance, then perhaps we need to really consider more robust hardware when we build data centers, right, that exhibit lower variance. For example, perhaps we should put in enterprise-class hard disks instead of consumer-class hard disks, because enterprise ones actually do display lower performance variance. Right? If intentional variance is a dominant source, then perhaps we need to reevaluate the trade-offs we make when making distributed systems. For example, using data center schedulers that emphasize predictability instead of resource utilization. And I think that we're already starting to explore some of these trade-offs. For example, from my perspective at least, the IQ talk from yesterday was one example of exploring this sort of trade-off of resource efficiency versus predictability, for example. So in conclusion, I think there's a lot of mounting evidence that predictability is important for large-scale distributed systems and cloud computing environments. Obviously, I'm not the only one who's saying this. Right? There are talks yesterday that talked about this too. But I wanted to emphasize this point because I'm working on my dissertation, which is on automated performance diagnosis. And I really like my work to have a lot of impact. But I don't think that this is going to happen unless the distributed systems that these things operate on are designed with slightly more predictability. They need to at least meet us halfway somewhere, right? And I might be wrong about this, right? And I hope so, actually. Maybe there's a magic sauce making systems more predictable. Perhaps there's a magic way to do performance diagnosis that I haven't thought of yet. And if I'm wrong about it, I really hope so. And I'll come back and I'll buy everyone a Diet Coke in 5 years. So let's do that, right? But until that time, I think there's a lot of interesting research that can be done in identifying where variance comes from in distributed systems and data centers, and building tools and techniques to help developers build more predictable systems. Thank you.